All right. Well, I see a lot of people are here. You know, I've gotten the emails and seen that we had to jump online for today. And so, again, this is Dr. Harper. I'm covering for Dr. Hartman today. And we're going to take a look at capacitors and do a few capacitor problems and look at the in-class problems and the web work problems. And then Wednesday, we'll start looking at the first order DC transient circuits. So, all right, let's just get started. Hopefully you can see my OneNote screen. That's what I believe I have it set up for. And so the symbol for capacitor is just a couple of parallel lines, trying to mimic the actual physical construction of a capacitor. We use the variable C for capacitors, just like we use L for inductors. And the units are in farads, where we use a capital F. And these are named after Michael Faraday. And so the units are in farads. And you can expect to see some pretty small numbers. The type of farads that we typically use are millifarads, microfarads, nanofarads, and even picofarads. So just to expect to see some pretty small numbers in typical applications of farads. There is a voltage across a capacitor, and there's a current going into the capacitor. And this is something we just need to chat about for a few minutes. As Dr. Hartman pointed out in the video, the capacitor is made up of two parallel plates with a gap in between them. And so, you know, you might be saying, well, how can current flow into something that's got a gap that doesn't allow current to flow? Current does flow into a capacitor, and the charges just pile up. The positive charges pile up here on the top plate of the capacitor, the positively charged plate, and the negative charges pile up on the bottom of the capacitor, and there's a separation of charges there. That's what gives us the voltage. And so positive charges flowing into the top, negative flowing into the bottom, that's current flowing. So there's current flowing into the capacitor from both sides. It's just that the current doesn't go through the capacitor. And a good way to think about it might be to look at a water analogy here. If we look at a pipe where we can normally flow water into the pipe and through the pipe and come out the other end, in the water analogy, the water in motion is current, and voltage is a pump that's providing pressure that pushes the water around the circuit. That's analogous to voltage in a circuit being the push behind the charges that are moving, creating the current that's flowing. And if we were to take this pipe where normally we flow water through the pipe, and we put a membrane in here, a rubber membrane, and we seal it all the way around, then we can still flow water into the pipe, but it hits this membrane and it doesn't flow out the other end, but the membrane just sort of stretches. And the water keeps stretching this membrane, and so the membrane is storing up energy with this water coming in. If we're still holding pressure there but stop flowing the water, then the membrane just sits there, you know, with this being stretched and having this water in it. But then if we turn it around and let the situation go, stop the pressure on the pipe going in, then the membrane will come back and it'll push the water back out the other end of the pipe. You know, it'll release the water back into this water system. And so that's the way a capacitor works. We pour the current into it, the charges pile up on either side of the plates, and then if we let that go and stop charging up the capacitor, it's really just a battery. And it turns around and releases the positive charges back into the circuit through the top and the negative charges back into the circuit through the bottom. So it releases current back into the electrical system, just like a battery does. So you can think of a capacitor as just a short-term battery, something we can charge up quickly. It holds the charge for a little bit, and then it can release the charge. So that's how a capacitor works, and hopefully maybe just having the water analogy will help you picture all that. The important equations, of course, are that current is equal to C times dV dt. So just like we had V equals L di dt, here we have I equals C dV dt. So the current in a capacitor is proportional to the rate of change of the voltage across the capacitor. And then, of course, the voltage then is 1 over C integral of I dt, plus whatever constant it takes to make the initial conditions work. And here, we don't like to use the C for the constant of integration here because we already got a C in here. So sometimes we like to use K, or some people use other variables, but just something to indicate a constant for the integration. So that gives us the volts. And then power, of course, is always going to be voltage times current if we have both of those, like you will with the graphs. Or substituting in, we can use C VC dV dt. And that would be in watts. And then energy is just 1/2 CV squared in joules. So those are our 4 equations. Hopefully they look very familiar to you. They look very similar to the inductor equations that we developed on Friday. And so there they are. They are very similar, and hopefully very easy to work with because you've seen these equations for inductors. Because of this original relationship that I C dV dt, then we can say, and like what Dr. Hartman pointed out in the video, in a DC circuit, when the voltage is not changing, then there is no current. So in a DC circuit, a capacitor behaves like an open circuit. An inductor behaved like a short circuit because there was no voltage. A capacitor behaves like an open circuit because there's no current when everything is a constant. So we'll want to look for that in any DC circuit right off the bat to see if that's what we're dealing with. Then we know we can treat the capacitor like an open circuit. And we will be making use of this starting on Wednesday when we look at these transient circuits, because we are going to have DC circuits. And we will be looking at them and saying, all right, the capacitor in this part of the circuit behaves like an open circuit. Then we'll throw this switch or something and make some changes. And the other observation we'll make is that the voltage across the capacitor can't change instantaneously. The current through an inductor can't change instantaneously. You can't have a jump in the graph. You can't have a discontinuity anywhere. It has to remain a continuous function. And the same is true for the voltage across the capacitor. That has to remain continuous and constantly differentiable so that there are no discontinuities in the voltage across the capacitor. And so we're going to take advantage of that too on Wednesday when we start looking at DC transient circuits. Let's just look at a couple pretty straightforward problems here that are the ones that I have as examples. If we look at a series loop here with a current source and an inductor and a capacitor here, and this current source is IS of t, we have 10 millihenries here and 10 microfarads here, then this current flows around this circuit in a clockwise fashion, and it creates a voltage here that we call VL of t, and a voltage here that we call VC of t. Creates a voltage across both of them. Suppose we're told that the current in graphical form looks like this, where it just goes up in a constant fashion, and that one point right here is that we have 0.1 amps at t equals 1 millisecond. So the time axis is given down here in milliseconds, and this is IS of t in amps. Then we could look at this one, for example, and we could look and say, okay, well, I can get the slope of that line. It's a y equals mx plus b equation, and b is 0 because it's going through the origin. And so it's just y equals mx and the slope. And the slope is the rise over the run, so the slope is 0.1 over 0.001, and that comes out to be 100. It has a slope of positive 100. So the equation of this line is that I S of t equals 100t. Y equals mx. So that's what that graph gives us. And let's see, suppose we come back over here and we're told the initial condition of this capacitor is that it has 0 volts across it at t equals 0. Then we could compute the voltage across both the inductor and the capacitor from that current that we're given. The voltage across the inductor, VL of t, of course, is L di dt. That was our equation from Friday. And so we put in our value of inductor, which is 10 times 10 to the minus third, L, and then multiply it times di dt, which is the slope, which we already looked at was 100. So we just multiply those two together, and that comes out to be a constant of 1 volt. And then if we looked at the voltage across the capacitor, well, we've got an equation for that too. It's 1 over C, the integral of I dt. And so we'd have 1 over the 10 times 10 to the minus 6 for microfarads, and then the integral of 100t dt. And that works out to be 50 t squared over 10 times 10 to the minus 6, which comes up to be 5 times 10 to the plus 6 t squared volts. And checking the initial condition, that comes out to be 0 at t equals 0, and that is what the initial condition is. So we don't need a constant of integration to match our initial conditions because, well, we don't. So that's the kind of thing we do there. We integrate or we differentiate depending on what we've got, and we figure it out, and then Kirchhoff's voltage law still holds. So, for example, if we wanted to know Vs of t here, the voltage across the source, well, then we could just do KVL around the loop and add these two together to get the voltage across the source, because that's what KVL around the loop says would happen. So a single loop is still a single loop. It still has one current in it. There's voltage drops across each element. You can do KVL around the loop. All of that stuff still holds. So, looking at one where things are in parallel, where we might know Vs of t, or have a Vs of t, I should say. We don't know it. But maybe we've got a resistor and an inductor and a capacitor. And in this case, we have 1 ohm, 1 Henry, and 1 farad. The initial conditions are that Vc of 0 is 10 volts, and IL of 0, the initial condition on the inductor, is 0 amps. There's a current that leaves this source, and then there's a current that goes down in every branch. There's current through the resistor we might call IR, a current through the inductor we might call IL, and a current through the capacitor that we call IC. And of course, the current going into the top node, IS, is equal to the currents leaving the top node, IR plus IL plus IC, just like we always did with single node pairs, which is what this is, what we have when things are in parallel. If we knew the voltage, if we knew Vs of t, then we could compute each current, because everything shares the same voltage. When things are in parallel, they share the same voltage, even if they're inductors or capacitors. In that respect, they behave just like resistors, connected to the same voltage source. In this case, we're actually given that IC of t equals 5 amps, a constant, for t greater than 0. So instead of being given the voltage, we're given one of the currents. And if we have that current, or once we have that current, then we can compute the voltage, because from that current, we can get that Vc of t, the voltage across the capacitor, is 1 over C integral of IC of t dt. And so we have 1 over 1, the 1 farad capacitor, and just the integral of 5 dt. And so that just comes out to be 5t plus our constant. at 0, this works out to be 0, and we're told up here our initial condition is that VC at 0 needs to be 10 volts. So from that we can see that K, the constant integration, needs to be 10, so that we have 5t plus 10 volts. And that would be this voltage right here across the capacitor, but that's also the voltage across the inductor, the voltage across the resistor, and Vs of t, because everything in here shares that same voltage. And from that, we can find that, voltage, the current through the resistor, IR of t. Well, we know the voltage across the resistor, we know the value of the resistor. All we need here is Ohm's law, just V over R. So we take our 5t plus 10 volts, and then we divide it by our 1 ohm, and this just comes out to be 5t plus 10 amps going down through the resistor. And for IL of t, we have an equation, 1 over L integral of VL of t dt. And so we have, again, the 1 over the 1 of Henry inductor. And now we need to integrate 5t plus 10 dt to get our expression for the inductor current, and then check to see what initial condition we may need there. So this comes out to be 5/2 t squared plus 10 t amps. And again, at t equals 0, this comes out to be 0, and our initial condition on the inductor is that it's 0 amps. So we don't need a constant there. And so now we know IR, we know IL, we know IC, because that's what we were given to start with. So if we wanted to write out IS of t, it would just be IR of t plus IL of t plus IC of t. And so that would be 5t plus 10 amps through the resistor, 5/2 t squared plus 10 t amps through the inductor, and then just 5 amps constant through the capacitor. And putting all that together, we have some like terms here. So looks like 2.5 t squared out front plus 15t there, and then just 15 on the end amps. So fairly straightforward examples, just to show that series and parallel still work. Ohm's law still works. KCL and KVL still work. Everything we've learned about circuits still holds here as we add these capacitors and inductors into them. So then turning over to the in-class problem, we do need to take a look at in-class problem 1, part A. Because in that problem, it says, let's find a maximum energy given a voltage. And so the first thing we were hoping you would infer from this problem is, well, if I'm looking for a max energy, that's going to happen wherever I have my max voltage. Because remember, energy is just 1/2 CV squared. So the 1/2 is a constant, the amount of capacitance is a constant, and so all I got is V in there. And so wherever that voltage is a maximum, that's where the energy is going to be a maximum. So for this problem, it really boils down to saying, well, where does the maximum voltage occur? And the voltage that we're given is this expression 5 plus 3 cosine squared 200t volts. And every year in every class, we get a lot of questions about this one, and people ask, well, how am I supposed to figure out what the maximum of that is? Am I supposed to take the derivative of that and set it equal to 0, or what? And really, one way you could do it is just to look at it graphically, right? If we were to just look at this for a second and say, all right, if I started with cosine, well, then cosine might look something like this, because I know what cosine does. And cosine just sits here and goes back and forth between +1 and -1 at some frequency. And that's what it does. Just varies between plus and -1. If I took a look at that and then said, all right, let's square that. Let's come up with cosine squared. Well, then we just take that, and 1 squared is still 1. And then everywhere it was negative above, it just becomes positive. It goes to -1 squared, which is 1. And then it just stays positive the whole time between 0 and 1. And so that's maybe what a cosine squared would look like. And 3 cosine squared means I just multiply the amplitude by 3. So it goes between 0 and 3 as it bounces along there, being always positive. And then if I say 5 plus 3 cosine squared, then I just add 5 to this axis, or 5 to these bottom values, and 5 to the top values. And all that really does is shift everything up by a constant, so that this is 0 down here, and now what was 0 here is 5, and what we're bouncing up to at each peak here is really just 8 volts. So 5 plus 3 cosine squared at some frequency is going to be a graph that looks like this, and from that graph we can pull off the maximum voltage and use that to compute the maximum energy. So that's part A. Part B, you're given a current there, so you just need to integrate that, and you're given an initial condition. So hopefully that's pretty straightforward. And then problem 2 on the in class, you're given a current graph, and so we've got to figure out the voltage from that. And the equation for capacitors is that V equals 1/C integral I. So we've got to integrate that graph. And once again, you would hope that we would give you some nice geometric shapes so you wouldn't have to come up with equations to integrate mathematically. And when I look at this thing, I see a nice triangle, I see a nice rectangle above the x-axis, and then I see a nice rectangle below the x-axis going out to 5 milliseconds, because that's all we need to really do is integrate this thing out to 5 milliseconds, because all the other questions are between 0 and 5 milliseconds. So hopefully you can use the area under the curve technique and come up with the graph of the voltage. And then once you've got your 2 graphs, of course, you can come up with your power, and energy is again just 1/2 CV squared. So you can see what's going on there. And then the third in-class problem is just 2 problems, one with the switch open and one with the switch closed. So a little different combination of things in the middle there. But remember, the thing you have to remember about capacitors is that when you combine them together, capacitors in series, you use the inverse equation, and capacitors in parallel, you just add up. So they work opposite of the inductors and the resistors. So you already know what to do, you just need to know when to do it. When to use the right equations of adding and the sum of inverses and the inverse of that final sum. And so with capacitors, the ones that are in series do the inverse, and the ones that are in parallel just make them simple. So hopefully that's pretty straightforward and won't give you too much trouble. I would like now to flip over to WebWorks. Problem there. So open up WebWorks here and share that screen. So here for homework 12. The first problem, just using the standard equations for capacitors. Here's a cosine squared, and so I believe that one is asking you to look that up on a calculus book or something and find the right equation for the derivative. You need the derivative of that, and or you may already know it from your math classes. I don't remember it, so I'd have to look it up, but that's what we're asking you to do. And so that's the first web work problem. And then the rest of these are just exponentials. And so that's pretty straightforward, whether we have to integrate or differentiate. That should be no problem. The next one is doing some equivalent inductance here. So first starting out with inductors where things combine like resistors, and then the same layout but with capacitors so that you can practice doing the opposite relationship. We've got this one up here to compare against and say, well, whatever I did up here, if I did it in series and added them, then down here I'll use the inverse equation, and then whatever I did up here in parallel, down here I'll just add. So just to have them side by side there for you to play with is a good one. This next problem, the single loop problem, and so you're given here the voltage across the capacitor, and it's a cosine function. And so obviously, since this is a single loop, it would be nice to know the current, and we can get that from just C dV dt here, and that's taking the derivative then of this cosine function, and that'll give us the current. And then we can use that current is flowing here through this inductor. We can use it to get the voltage across the inductor, because that's just L di dt. And so we can get that voltage across the inductor, and then we can put those two together to find Vs, because we can just use KVL to run the loop here, and that'll give us the total voltage. The next one is a graph problem, as I recall. And so this one, I think we give you the voltage across the capacitor. Yes, and so it's a 20 nanofarad capacitor. And so to get the current, you just use C dV dt. So you need to find the slope of these lines. And then please notice that the units are in millivolts and milliseconds here. It's hard, maybe hard to see on the graph, but that's what it's repeated up here in the problem, that the voltages are in millivolts and the time axis is in milliseconds. So once again, we'd like you to draw all three remaining graphs, the current, power, and the energy, and then you should be able to go in and pull out these times, find the points at these various times on the graph, various different graphs. So hopefully very similar to the inductor problem that you've had a chance to look at already. This last one is one that we get a lot of emails on every year, so I'd like to look at this one with you real quick. We're given this voltage over here, and we have a single pair circuit, single node pair. We have some things in parallel here, so things share the same voltage. Clearly, the inductor, the 20 millihenry inductor, shares the same voltage. Now, neither of these capacitors, the 8 millifarad or the 24 millifarad capacitor, don't share this voltage. But if we combine them together, then we'd have something that would share this voltage. So that's what we need to do first, is do that. And then when we've got the voltage, we can find each current here. We can find the current down this capacitor branch, and we can find the current down this inductor branch. One involves a derivative relationship, one involves an integral relationship. It's when we do this integral out here, 1 over L integral V, to find this one. This is where we get a lot of the questions, is that you find the expression for this current out here, and then you look up here and say, there's my initial condition, so I'll just throw that in there, and I'll make that come out, and then when I do it, I don't get the right answer in web work. And what you got to pay attention to is that that's not the initial condition of the current through the inductor. That's the initial condition of this current coming out of the source back here. And so then we get a lot of people emailing us and say, well, how does that help us? What we need is the initial condition over here, and you didn't give that to us. How are we supposed to work this problem if you don't give us the initial condition through the current, through the inductor? And so the idea is, well, if you don't know it over here, you don't have enough information to solve for the initial condition through the inductor when you come up with this equation, then you carry it as a variable. We don't know it yet, so, or we can't solve for it yet, so carry it along and come up with the equation for this current with that variable in it, come up with the equation for this current, which doesn't need such a variable,
and then add those together to get IS of t. Now you've got an expression for IS of t, and now you've got an initial condition for IS. So plug in this time t equals 0 to that final equation, and that's when you can get your constant of integration. So take a look at that, make sure you understand all that, and see how all that's working, and see how you can use an initial condition somewhere else in the circuit to solve for an initial condition that you need where you do your integration. Because this is a good little circuit right here. If you've got a good handle on this one and what you have to do here to make this work, then you've got a good handle on capacitors and inductors coming out of this series of lectures, and you'll be ready to move into the first order DC transient problems starting this Wednesday. And again, the next test is 2 weeks from tonight. So it'll start with Thevenin and Norton, and it'll cover inductors and capacitors, and it'll cover these DC transient circuits that we're going to start looking at Wednesday. So this will be a major part of the next exam. So please make sure you use these web work problems to make sure you understand all that. All right. Well, I ran through all that pretty quickly, just because I'm sitting here at home and don't have a lot of material that I had in my office, and so I just grabbed a couple of example problems and brought them with me. And so if you don't have any questions, we'll end it there. If you have some questions, holler out or use the chat.
All right. Well, hello, everybody. Dr. Hartman here. I'm filling in for Dr. Hartman today. Just have a quick lecture for you, real quick, to look at some things with capacitors. Take a look at the in-class problem and the web work problems, and hopefully get you on your way. And then move on to some first order DC transient circuits on Wednesday. And we'll look at those through next week. The next test, of course, remember, is 2 weeks from tonight. So we're working our way towards that pretty rapidly. And hopefully you can stay caught up and deal with the web work and these in-class problems. All right, I'm gonna shift over to my OneNote screen here and do some things there. I'll try to keep my eye on the chat if anybody has any questions, and then see where we go from there. All right, so capacitors. We draw them as the two parallel lines, trying to match the shape of them, of course, an actual capacitor. We use the variable C for them. We use L for inductors, as you saw on Friday. We use C for capacitors, and the units are in farads. We aim for microfarad, so we use a capital F for those, and you should expect to see typical applications use millifarads, microfarads, nanofarads, and picofarads. So farad's a pretty big thing, and we have to use some pretty small units when we talk about any practical capacitors. There's a voltage across capacitor we still talk about, and we talk about a current into the capacitor. And that's something we need to look at just briefly here, because a capacitor is two parallel plates with a gap in between them. And so we have to make sure we understand what we're talking about when we say this current into the capacitor. And so, as Dr. Hartman mentioned in the video, what happens with this device when we hook it up is that you can direct a current into it, but because of the gap, the current doesn't actually flow through it. You just end up with positive charges piling up on the top plate and negative charges piling up on the bottom plate, and this gap separating the charges. It's that separation of charges that creates this voltage across of it, across the capacitor, and gives us that value. So when you're pouring current into it, you're really, you're attracting the positive charges from the top and the negative charges from the bottom. So the current doesn't flow through the capacitor, but current still flows, if you will, and just separates these charges. And then when you stop charging it up and allow the energy to be released, it turns around and releases the current back into the circuit. The positive charges flow back this way and the negative charges flow through the bottom, and current is able to go back into the circuit. So in all essence, the capacitor is really a battery. It's just sitting there as a short-term battery. You can charge it up when you put current into it, and then when you turn around and let it go, it releases the current back into the circuit just like a battery would if we hooked it up there. Its problem is that it just can't hold the charge for very long, and so it releases the charge in a very short period of time, and then it's all done. It can't maintain it for across a long time period. A water analogy, if we were to look at that real quickly here, sometimes helps visualize it. If we've got a pipe here and we let water flow into the pipe, that's analogous to current. Water in motion is same as current in motion. And voltage is the same as a pump in a water system. It provides the pressure that pushes the water around the system, like voltage is the pressure that pushes the charge around the system, and so causes the current to flow. And so normally we got a pipe here, we pour water in one end, it flows out the other end, everything's fine, just like current flowing down a wire. With a capacitor, it's as if we put a rubber membrane inside this pipe and sealed it all the way around. And now when we pour water in, instead of it flowing through and coming out the other end, this membrane just stretches, right? We're able to store up energy in this membrane, and if we keep pushing water in here, then the membrane just keeps stretching down the way, but the water doesn't flow through the pipe anymore. And if we hold pressure there, we can hold the membrane at that case. And then if we let the pressure go and allow it to release, well, then it'll push water back out of the pipe and back into the system. So membrane in a pipe is like a capacitor in a circuit. So that may help, at least I hope it does, when you're thinking about capacitor. All right, so the governing equation here is that the current through the capacitor is equal to C times the derivative of the voltage across the capacitor. So I is C dV dt, just like V was L di dt last Friday. So a very, hopefully, similar looking equation to what we had for inductors, and similar relationship here. So I is C dV dt, and then in that case, the voltage across the capacitor is going to be 1 over C, the integral of I dt, plus whatever constant. And here, whenever we write the constant, sometimes people do different things. Some people use prime marks or numbers, but you know, we've already got a C in this equation. We've got 1 over C for the capacitance. We don't like to use just another C for the constant of integration. So one technique is to use maybe a K out here to be the constant of integration, just so we don't think we're adding in a capacitance value. And so, and that would be volts. And then power is always voltage times current if we've got them, like we do when we have the graph problems. So it's also equal to C, V, C, and then dV, dt. So just by substituting in the I, we can have an equation where we have CV, dV, dt, much like we had Li, di, dt. And then energy for a capacitor is just going to be 1/2 C V squared, the voltage across the capacitor. And those are watts and those are joules. So those are our 4 equations. They're perfectly symmetrical to the equations we had for the inductor. So I hope you see that there's really nothing new here. It's just the same equations, but using C for the capacitance, and everywhere we had current before we got voltage, and vice versa here. So if you've gotten comfortable with the other 4 equations, hopefully these look very comfortable to you as well. Because of them, because of that first equation there, we can say in a DC circuit, a capacitor behaves like an open circuit. Okay. We said that in a DC circuit, an inductor behaves like a short circuit because, in that case, if the voltage, if the current's not changing, there's no voltage. Here, if the voltage is not changing, there's no current. And so, since we're proportional to the rate of change of the voltage, if the voltage is ever a constant, then it means that the capacitor is fully charged up and there's no more current flowing into it. And in that respect, it behaves just like an open circuit would. No current flows into it. The voltage is equal in the capacitor and the rest of the circuit. And so you've got two things at equal potential. That's the same as like having water at the same level. And if you hook up a pipe between two buckets of water at the same level, then nothing flows between them because there's no difference in pressure there, no potential. So when a capacitor gets fully charged and the voltage stops changing, then the current just stops, and that makes it behave like an open circuit. So we're going to take advantage of that on Wednesday when we start looking at these DC transient circuits, because they will be DC circuits. And at times in there, quite a bit of time, the capacitors are going to behave like open circuits. And then the other thing we have is, because of this derivative relationship, the voltage across a capacitor can't change instantaneously. We can't have any discontinuities in our voltage across the capacitor, because if we did, the derivative would be infinity, and we can't have that. And so the voltage across the capacitor has to stay continuously differentiable at all times, and so it can't have any jumps in it. And so when these DC transient circuits we start looking at on Wednesday, we're also going to take advantage of that. We're going to throw a switch and a lot of things are going to change, but we're going to go find our capacitor and say, that one doesn't change. That voltage has to stay continuous as we make this change. So right here at t=0, when we throw this switch and lots of things change instantaneously, the voltage across the capacitor won't, and we will start building our new circuit there for after this switch is opened or closed and things have changed. We have to hold on to our capacitor voltage. So that'll be a key for these DC transient circuits. But until we get there, we're going to look at some more, or do some problems, both on the in class and then on the web work, where we just take advantage of these equations, the equations we have here for capacitors. So let's look at this one real quick. A fairly simple little example here with a current source and an inductor with its coil and a capacitor with its parallel plates, and current that's driving this single loop here, and that current is given to us in a graphical form where it just goes up continuously in a straight line, starting at 0. So y equals mx plus b, and b is 0 here. So this is is of t. It's in amps, and we're given a point here on the y-axis of 0.1 amps, and we're told that that occurs at a time of t = 1 millisecond. The time axis here is given in milliseconds, and so we can look at that, and there's a couple of things we can tell from that. So we'll come back to that in a minute. Let's finish the circuit. It's a 10 millihenry inductor. It's a 10 microfarad capacitor. The current that's flowing around this circuit in a clockwise fashion, we would still put the voltage here and call it VL of t, and put the plus sign of the voltage here and here and call it VC of t, just like we would if they were resistors. We draw the current going into the plus terminal of the devices, the voltage across the devices, and we can still use KVL around it, so we can still say that there's a voltage across the source here, and Vs of t has to equal VL of t plus VC of t, because that's KVL around the loop.
here. And we can take advantage of the fact that there's a single current, and we know it everywhere, so we can apply it to find both of these voltages. The first one for VL of T, we've got an equation from last Friday, and it's just L times di dt. So we need the slope of this line over here to find di dt, and so we can multiply that by the inductance. So we come back over here and look at it and say slope, the rise over the run, we got 1 point for the rise and the run for that. So it's 0.1 over 0.001, and that comes out to be a value of 100. So the derivative of this line, the slope of this line, is a value of 100. So when we do L di dt, we'd just be taking 10 times 10 to the minus third times 100, or 1 times 10 to the second, and this just comes out to be 1 volt. Okay. So the voltage across the inductor that is induced by this current just works out to be a constant of 1 volt. Now, if we were going to compute the voltage across the capacitor, we've got an equation for that too, and it's 1 over C integral of I dt plus whatever constant. And so we'd do 1 over the 10 times 10 to the minus 6th, and the integral of this line. Now we need an equation for this line, but again, it's just y equals mx, where b is 0. The y-axis is current, and the x-axis is time. So the equation of this line is that I of t equals 100 t, and that's in amps. And so we're going to integrate over here 100 t dt, and then again plus whatever constant. Now, for that we need the initial condition, and we were told, let's suppose that Vc of 0 is 0 volts. So we do our integration here. We have 1 over 10 times 10 to the minus 6th times 50 t squared. And then we look to see what we might need for a constant, and we can see that at t equals 0, that's going to be 0, because we've just got something times t squared, and the initial condition is 0. So our constant of integration is just a 0. So we'll just multiply this out here, and this comes out to be 5 times 10 to the plus 6 t squared volts. And so now we have VL and VC, and we could add them together to get VS. So just hopefully pretty straightforward there for a series loop. If we looked at a single node pair, if we had maybe a voltage source in parallel with a resistor, an inductor, and a capacitor, then our resistor is 1 ohm, our inductor is 1 Henry, and our capacitor is 1 farad. It's just going to make the math come out to be nice. Our initial conditions are that Vc of 0 is 10 volts, and IL of 0 is 0 amps. The initial voltage on the capacitor is 10 volts, initial current through the inductor is 0 amps. In this problem, again, since everything is in parallel, we've got a current that leaves this source, goes up into the top node, if we will, and then leaving the top node, we've got IR of T, the current down through the resistor, we've got IL of T, current down through the inductor, and IC of T, current down through the capacitor. And by Kirchhoff's current law, IS of T is equal to IR of T plus IL of T plus IC of T. The currents leaving the top node have to be equal to the current going into the top node. So just to show you that even if we have inductors and capacitors, series loops hold, and KVL holds, single node pairs hold, and KCL holds. Everything we've learned up till now about circuits is still valid. We have not invalidated anything about it.
For these, everything's in parallel and everything shares this common voltage here, Vs of t. If we knew that, we could figure out all the currents. In this case, they give us one of the currents. They tell us that IC of t is 5 amps for t greater than 0. And so that's where we start. That we go out and say, all right, if I know the current through this capacitor out here, I can compute the voltage across that capacitor, which would be right here. And that is the voltage that everybody shares. Everybody's in parallel. So if I know that voltage, that's the voltage. So Vc of t is just, again, 1 over c integral of I dt plus whatever constant I need. And so in this case, it's 1 over 1 farad. That comes out nice. And then we just integrate 5 dt, again, plus k. So we've just got 5t, essentially. 1 over 1, and the integral of 5 just comes out to be 5t. Now at t equals 0, that comes out to be 0, and we're told the initial condition is 10 volts. So we'll need a constant of integration that's just 10 here. So the voltage that everything shares in here is 5t plus 10 volts. So with that, then, that's the voltage across the resistor. That's the voltage across the inductor. So for IR of t, the current that's going down through the resistor, we go back to the law we have for resistors, which is Ohm's law, that we just need V over R. So we have 5t plus 10 over 1. So just 5t plus 10 volts, amps across through the resistor. And for IL of t, our equation is 1 over L integral of V dt plus some constant. And so we've got 1 over 1 of the integral of 5t plus 10 dt. So that comes out to be the 1 over 1 goes away. And so we've got 5/2 t squared plus 10t. And at t equals 0, that's going to come out to be 0. And our initial condition is that we have 0 amps. So our constant out here is just 0, so we don't need it. So this is our expression for the current through the inductor. And so now we've got IC of t up here, IR of t here, and IL of t here. And so IS of t would just be to add them all up. And so we'd have 5t plus 10 for the resistor, plus 2.5 t squared, plus 10t for the inductor, plus just a constant 5 for the capacitor. And that would be our total current. And to clean that up, just gathering together some loose terms, or some like terms, sorry. 2.5 t squared plus 15t plus 15. I think that's everything. Amps. Okay, so that's just sort of how we use our equations to solve for things. And the things we're looking for are things we already know how to do, like current through branches, voltages around a loop. So no change there. There is something we need to look at on the in-class problem, part 1A. The in-class problem, which I have right here, part 1A says to find max energy given that the voltage across a capacitor is expressed by 5 plus 3 cosine squared 200t volts. So this is sort of just an exercise in well, constructing some things. Max energy. So again, let's start with that and say, all right, energy for a capacitor, 1/2 CV squared. And here's our voltage, and that's the only thing that's changing. I mean, 1/2 is a constant, C is a constant. So we got the voltage that's changing. And to find max energy with this, hopefully we can say, well, what I need to know is where's the max voltage? Because that's where I'm going to get the maximum energy.
And so I need to look at this expression here, see what's going on here, and find the maximum here. And I can stick that value in right here and give you this constant value of maximum voltage. I'm sorry, maximum energy. So to find the maximum of this thing here, we just need to go back to the basics, you know, for cosine. And say, if I were to ask you to sketch out a quick graph of cosine, I know that all of you could sit here and say, well, cosine, that looks something like this. Starts at 1 here at t equals 0 and bounces back and forth between plus and minus 1. So that's cosine. If we need to know what that is. And so we say, okay, great, let's square that so that we can draw a quick graph of cosine squared. Well, it's still going to be at 1 here. That's 1 squared. And it's going to go down. And then here, where things start to get negative, it's going to become positive. And it's just going to turn around and be positive. Then we're back to this part of it here. And then again, this negative part becomes positive and positive and positive. And so cosine squared sits here and just goes between 0 and 1 and bounces along here in this bouncing fashion. And so that gets us to cosine squared. If we have 3 cosine squared, well, then that just bounces back and forth between 0 and 3. We multiply both of those values by 3. Yeah, and now we're bouncing around between 0 and 3. And that gives us 3 cosine squared. And if we take all that and just add a constant 5 volts to it, then what we're really doing is shifting this graph up 5 volts. So then instead of being at 0, 0 is down here, and this is at 5 plus 0 and 5 plus the 3. We've just added a constant DC voltage to everything. And so from this, now, hopefully this graph of 5 plus 3 cosine squared, we can find the maximum. The maximum is this peak here that the voltage reaches at each time. And it's that maximum that we need to stick in here to say, okay, that's where your max energy is going to be, this maximum voltage value. So hopefully with that little just analysis of a waveform that we haven't seen before, but just knowing how these things behave, we can figure out what this maximum voltage is. Part B of in-class problem 1 is asking you to integrate an exponential. And so you can hopefully do that. And it's got an initial condition, so you can make that happen. Problem 2 is a graph. And again, we need to have sketches of the other graphs so that we can find out what's going on at these points in time. They all are in, well, 1 millisecond, 3 milliseconds, and 5 milliseconds. So we need to go out to 5 milliseconds. There's really all we need. And so we're given current, and we need to find voltage across a capacitor. And that means we got to integrate. And so hopefully you can look at this graph and see a triangle and a nice rectangle above the x-axis, and then a small rectangle below the x-axis. And so we've got some positive areas and some negative areas there that are hopefully not too bad. And you can use the idea that an integral is really the area under the curve. And so you could integrate out to 5 milliseconds by just adding up the area above and subtracting off the area below the x-axis and coming up with the integral there, and then multiplying that by 1 over c so that you get your voltage. And then once you've got that, then you can have the graph of the voltage, then you can find power and energy. So hopefully that's not too bad. And then on the back side of the in-class problem is some equivalent capacitance, 2 problems there with the switch in there, and doing it once with the switch open and once with the switch closed. And just remember, when you do capacitance, all you need to remember is that things in series don't add together anymore. You use the inverse of the some of the inverses, like we do with parallel resistors and inductors. And things that are in parallel now just add. So with capacitors, you just need to remember you do the other way. You already know how to do each way. You just remember with capacitors, you do the other thing. And so hopefully that one's pretty straightforward and not too terrible. So take a look at those and play around with those in-class problems. And then
when it comes to the web work, there's some things going on there. So let me bring up the web work. We had, sorry. Homework 12. Okay, so I'm sharing the web work screen. Problem 1 here, just some standard stuff. At least parts C, D, and E are all using exponentials. Part A, again, is using cosine squared. And I think you've got to find the derivative of that, right? I is equal to C dV dt. So you've got to find the derivative of cosine squared. And so that one, because it's homework, it's easy, or hopefully you won't find it too bad. If you don't have it memorized from your math classes, to go look it up in a math book somewhere, or the inside cover of your math book. We won't ask you that on a test, so we're not asking you to memorize the trigonometric functions like this. So, but it's not too bad for homework because you got the resources. So hopefully that won't be too bad. You may know the derivative of cosine squared. I don't remember it. I'd have to go look it up. But either way, hopefully that won't be too bad. Then the rest of those are exponentials, and that's not too bad. Then equivalent inductance here, going back to the old way where inductors combine just like resistors, and then that same layout with capacitors. So you can see directly how things that combined up here in series, just adding together down here, use the inverse, and up here things that were parallel and needed the inverse, up and down here just add together. So you can have a direct comparison there and work on those and see the opposite relationships. The next problem, hopefully pretty straightforward. You're given the voltage here across the capacitor, and so it's a single loop. So since all we have is the voltage across the capacitor, about all we can do with that is find the current through the capacitor by taking the derivative of this, C dV dt. So taking the derivative of cosine and getting that. And then, of course, that current, because this is a single loop, that current's through this inductor. So we can find the voltage across this inductor with L di dt. And so we can get the voltage here, and then we'll find that it's pretty easy, if we've done everything right, to do KVL around the loop and add those voltages together to get Vs of t. So pay attention to that, to your derivatives of sine and cosine to get that. The next problem is a graph problem, and it's the current, sorry, the voltage across capacitor, find the current. So it's back to C dV dt. So again, we're just needing the slope of the lines here. And I'm stalling, waiting on web work to come up here. And it's not coming. So come on. Well, now's when I need a good story to tell you all while we sit here and wait, but I don't have a good story today. I also don't appear to have a good network. Okay, so here's the graph. Just need to find the slope of these lines. Again, pay attention to the units. It's written up here in the problem that we're looking at millivolts on the y-axis and milliseconds. Excuse me, on the x-axis. It's down here on the graph, but it's kind of hard to see. So that's why it's pointed out in the problem that we got millivolts and milliseconds here. So watch out for that. And then this last problem. This is one that we get emails on this every quarter. So let's just pay a little bit of attention to this one. We're given Vs of t here as an exponential millivolts. So we know this value here. And so we look across here and say right away, well,
great, I know the voltage here, but that's not the voltage across either one of these two capacitors. If you combine them together, it is the voltage across the equivalent capacitor. So that's where we start. And then it's also the voltage across this inductor over here, because everything's in parallel. We got a single node pair here, and I know the voltage across everything. So we ought to be able to find the current down through the single capacitor here with just C dV dt. That's pretty straightforward. And then we move over here and say, okay, I can find the current through this inductor. That's 1 over L integral V dt. And so I do that. And then here's where people say, okay, this one out here, I integrated out here. So that's where I need my constant of integration. I got to make this match. There's my initial condition. So they just throw 5 milliamps on for this expression out here. And then it turns out being wrong. And that's where the emails start. And they say, you gave us an initial condition, but then it turns out it doesn't work. That's why we got to look up here at this initial condition. We're not given the initial current through this branch out here, which is what we need when we take that integral, because we're computing IL here. This initial condition is given way over here for IS, the initial current leaving this source. And so as the emails go, you know, I point that out and say, pay attention to your initial condition. It's not for the inductor, it's for the source. And then I leave it at that. Then the emails come back and say, well, great, what do I do with that? How do I use an initial condition over here for the source to find this? I must find the constant of integration over here because that's where I integrated, and you don't give it to us. And so the idea is, you know, if you need it over here and you don't have enough information to find it because it's not given in the problem, then you carry it as a variable and say, all right, I'll figure it out later. There'll be some information later that'll help me solve for that. So you've got IL over here with its constant of integration that you need, but you don't know. So carry it as a variable and take that plus the current through the capacitor here, and those two together add up to be IS. And now you've got an expression for IS of T, the sum of these two currents over here, one of which has a variable in it. And then you can say, all right, now I have an equation where I have an initial condition, so I can put T equals 0 into that equation and solve for it. Once again, you don't just throw 5 milliamps onto that one and say, okay, I came up with this expression for IS of T, the sum of these two, and I threw 5 milliamps on the end, and that's still not right. Well, of course it's not right, because these are exponentials. And so when you have T equals 0, these are not going to be 0, and you just need to add 5 milliamps to get 5 milliamps. You're going to have something as the initial condition for this current. You're going to have something for the initial condition that this current at T equals 0, because they're all exponentials, and they're not going to disappear. They're going to have some mathematical value, and you need to solve for it. And so there's a lot going on here. And if you work your way through it and make sure you understand it, this is a good problem to finish up just the concept of inductors and capacitors in a circuit. If you get a handle on this one and can understand this one, then you'll be in good shape to put these two lectures to bed and move on now to the first order DC transient circuits that we're going to start with on Wednesday. So pay attention to this one. Make sure you understand all of it and see what's going on here and see how the math works, how you use the math with these derivative and integral equations to solve the circuit. Again, math is the tool we're using to solve this circuit. And so just pay attention to what's going on here and see that you understand this one clearly. And that'll be a good summation for it, because that's the last problem there. Okay, so with that, that's just all I had for you today. I'm sure Dr. Hartman would have had other examples to give you and would have gone through it, but that's all I had. And so that's all I had prepared to cover his class today, was just to use these little examples I had. So if nobody has any questions, either just by unmuting.
Could you do the first? Could you do the first problem on the in-class assignment?
Could I do it?
Right. Could you show us how to do it?
What? I mean, didn't I just do that? Part 1A?
Right, you showed like how to get it started, but I'm not really
Yeah.
sure what to do from there.
Okay, well, if you go back and look at this graph, I think you can find the maximum voltage on this graph right here. Um, um, Sitting right here. And so just find the maximum voltage here on this graph and put that into this equation, and you'll get your maximum energy.
Okay, all right.
And then, yeah, you can try and get those in class posted today, and then work on the web work. And try and stay caught up on that. Next test just 2 weeks away, so try not to fall behind on the web work. Try to stay up with it, and so you can ask Dr. Hartman questions, or myself if you need to email me, so that you don't have a lot to do there the few days right before the test. So just a few web work problems to come up with this. The DC circuits, we're going to be looking at those for 3 class periods. So we're going to look at them Wednesday and Friday and Monday. And then next Monday, we're going to have a lab over them. So we'll spend a fair bit of time looking at the DC transient circuits and how they work. And then once we finish up with them next Monday, we'll turn around and spend 2 class periods looking at op amps before the next exam. So, and remember, the next exam starts with the Thevenin and Norton material, because that wasn't on the first exam. So we start with Thevenin and Norton and go through next week. I need to talk to Dr. Hartman and see if op amps are going to be on the second test or the third. We've done it both ways, but it'll certainly go through the DC transient circuits that we're going to start on Wednesday.